Hi there. So we're back. We're talking about gravitational potential energy. This is probably our go-to potential energy when we're thinking about a lot of problems in this class. A lot of times we're changing the height of where we are in a situation, and that is going to change the potential energy, specifically the gravitational potential energy of this system. So I want to investigate a scenario that we have here. It's a very simple scenario. I'm throwing a ball up into the air. All right, I'm throwing a ball up into the air, and if I'm thinking about these interaction forces, right, I have an interaction force. I have, let's make it nice, an interaction force. All right, I have the force of the Earth on the ball, right? I have an opposite and equal force of the ball on the Earth. Now the Earth doesn't move much. It doesn't accelerate very much because of this. But it is perfectly fine to imagine, well, to even state that the ball doesn't just fall down to the Earth falls up to the ball. Right? That's a perfectly legitimate way of talking about things, not only in terms of relative motion, but also in terms of forces, right? We exert a force on the ball, and the Earth exerts a force on the ball, and of course the ball exerts a force on the Earth. Now, if we think about the change in the change in height, right? The change in displacement of distance, right, of position for this ball, we've thrown it up into the air, so it's traveling up. The Earth, right, the Earth doesn't really move much. We've already said that. But so we're going to use that approximation in just a second to make things a lot simpler. Let's talk about the works being done here. I have the work done by the Earth, and then I have the work done by the ball. All right, so by the Earth, right, this work is the force of the Earth on the ball times the change in position of the ball. And there's technically a dot product there, right? There's a dot product. We're going to talk about direction in just a second. But it's also key to remember that the force of the Earth on the ball really doesn't change a whole lot until we start getting to altitudes like far above Mount Everest, really. We're talking large amounts of altitude there to really change the force that a ball would feel from the Earth. So we're going to approximate it as a constant force. That's why we're not doing an integral here. If I think about the work done by the ball, right, that means I have the force of the ball on the Earth times the displacement of the Earth, which we just said was basically zero. Right? And if it's effectively zero, what we really can say here is that that the work done by the ball is basically zero. So while there is an interaction energy happening, or interaction force happening here, the energies are not necessarily going to be the same. So when I think about our definition now of the change in potential energy, and we're going to put a big G here just to show off that it is the gravitational potential energy, we're going to say that that's equal to the negative of the interaction works being done, right? The internal work. So I'm going to say that that's WE plus, well, WB was 0, so really it's just WE. Right? I could say 0 if I wanted, but yeah, there we are. If I expand this out a little bit, what is the force of the Earth on the ball? Well, it's the weight, right? It's just the weight for us right now. So I have MB times G times this delta YB, right, to get work. And then, of course, I need to have this cosine of the angle between my displacement vector and my force vector. This is actually really important, right? This starts to tell me something about if I'm gaining or losing potential energy here. Right? So let's actually break this apart, right? If I'm going up, right, if my delta y is up, then my force, of course, is down. I have a 180 degree difference there, or a 180 degree angle between those two vectors. I'm going to say that the cosine of 180 is -1, but I have this -1 floating outside of this parenthesis, this term here. So I'm going to actually have a positive change in potential energy, right? But if I'm falling back down, my delta y points down, of course FG still points down. Now I have cosine of 0, that's +1, and again this floating negative sign out here makes the change in potential energy negative. I'm losing potential energy. So let's actually just kind of write down these rules here, right? If we're going up, then cosine of 180 is -1, right? So I have delta UG, let's make it uppercase G, is going to be positive. I'm storing energy in this interaction between the ball and the earth. If going down, right, then really I should have said theta was equal to 0 degrees. Let's just quick change that up over here. I'm going to say then theta equals 180 over here. The theta equals 0 degrees if we're going down between the force and the displacement. Delta UG is negative. Let's just quick talk about that for a second. Where do we get or lose this energy to? If I think about this situation, right, if I throw a ball up into the air, I get slower and slower and slower until I stop, I turn around, and I come back down, and then I'm accelerating, right? I'm speeding back up. So it's probably coming from kinetic energy. I'm transforming kinetic energy into potential energy. I'm storing that movement, right? I'm storing that motion energy in an interaction. And then at the top, when I have only potential energy, then I get to convert it back down into kinetic energy again. We're going to talk about that a little bit more in the next in the next lecture. I don't know, man. It's been a day. Anywho, have a good one. I will see you next time. We're going to talk a little bit about conservation of energy. Thanks for watching.